So here was our mixing problem differential equation from last time. We used S as the dependent variable last time to represent the amount of salt. Now I'm just going to go ahead and call it Y. And yes, it does refer to the mixing problem, but I'm not going to think about the application really much. Let's actually change the initial condition to be something different. We used Y of 0 equals 0 before, representing no salt in the tank. Let's let it be something relatively large this time. Oh, I don't know, how about 200? In the application, that would represent 200 pounds of salt in the tank right away. Boy, yeah, that would be a lot of salt, really, really salty water. So this is going to be the IVP we're going to think about here. And what I'd like to do is I'd like to start off by thinking about this IVP in ways that we've done before. I will once again show you how to solve it with integrating factor. We'll make the slope field. We'll draw on the solution curve. Actually, well, I won't do the integrating factor because we've done that enough, but let's get Mathematica to solve it, make the slope field, draw the solution in the slope field, and then start talking about Euler's method again with a particular attention on errors and the error-bound theorem. So we'll save time with Mathematica here. You should be able to solve differential equations with separation of variables, with integrating factors, and with undetermined coefficients on the final exam. But let's use Mathematica. Dsolve or dsolve value is something you should be able to use as well. Again, dsolve value produces the output in sort of a nicer form. I will go ahead and define my right-hand side function here as well. My f of ty function is 12 minus 4y over 10 plus 2t. My first order differential equation is what you see there on the paper in Mathematica. Put it inside a list as y prime of t. Don't forget to use double equal signs. And if I've got f of ty defined, I can just type the right-hand side as f of ty, but replace y with y of t so that you're emphasizing to Mathematica's syntax conventions that y is a function of t. And then the initial condition, something other than what we did before. I'm using 200 this time. Again, use double equal signs. Outside the list, put a comma, y of t, comma, t, to emphasize we're trying to solve for y of t, and yes, the independent variable is t. There's the solution. It looks fairly nice. Sometimes you might want to simplify it. It doesn't change it in this case, or you might want to expand it. That does change it, but I think I like that less. Those kinds of things can be done to rewrite the solution function in different ways. And we could give this function a name, as we can always call it a phi. I can do escape, ph escape to make a phi. Escape, ph escape makes a phi of t. I won't bother with the subscript here. I'll just copy and paste this right here and enter that so that I've got the solution. And then I could use this to evaluate how much salt is in the tank when it's full. What was that, after 30 minutes, I think? There it is as a fraction, as a decimal. There it is. This is a different initial value problem. We should expect a different answer here. Was it after 30 minutes or was it longer? I'm forgetting. We could get more decimal places as well if we wanted to. I forget how long it took to fill up. It might have been 45. Maybe it was 45. That gets closer to 200. In fact, it gets over 200 in this case because we started with a lot of salt in the tank to begin with. Let's make the slope field, draw the solution curve in the slope field, show combines graphics. So the first thing we're going to make is the slope field with vector plot. And the second thing we're going to make is a plot of the solution with plot. For slope fields again, inside a list, put a 1 first, then a comma, then your right-hand side function. And that'll make a slope field, though, with arrows. Doing vector scale, arrow, was it arrowheads? 0 or something, I think like that. Let's get rid of the plot for the moment. Oh, I forgot what it was. Is that right? I should look it up in another one here. Let's look it up in a previous one. Did we make it here? Vector style arrowhead 0. Okay. Vector style instead of vector scale. There we go. There's our slope field. Now I'll put the plot back in there. Plot the solution function phi of t going from 0 to 200. Plot style, say thick and red. There's our solution. This particular solution decreases before it increases because it's so salty to begin with. The salt coming in is less concentrated than the salt that's already in there. So as it gets well mixed and flows out, the amount of salt actually goes down before it goes back up again. But in the long run, it still approaches, after 45 minutes, pretty close to 200 pounds of salt in the end. So that's the true solution to the differential equation, to the initial value problem, the true unique solution, in fact. Let's quickly apply Euler's method, and then we'll talk about the error-bound theorem. So once more, with Euler's method, we want to apply nest list to a function that I, just out of habit, call EM in honor of Euler's method. This is a two-dimensional function. This is the way that I do it. I'm not claiming this is the only way to do it. It takes two-dimensional input and gives you two-dimensional output. In general, maybe I want to put what h is here first, say 0.1. Then I can type the code as t plus h and w plus h times f of tw. Right? That's effectively, this is the recursive equation for Euler's method without subscripts. But you don't need subscripts here because that's just a notational convention to keep track of the fact that we're making a sequence. But as far as Mathematica is concerned, you don't need subscripts. I am updating the value of t as well by h each time. And this is the thing that gets iterated with nest list, EM, based on your initial condition, which is t is 0, y is 200. And if we want to go out to time 45 with a step size of h equals 0.1, I have to do 450 steps. So this will produce a lot of data and predict that after 45 minutes, after 450 steps, that the amount of salt will be about 201.704. Again, phi of 45 itself is that. So the error in this case by the last step would be 201.8 minus 201.704, an error of about 0.096. We might wonder, what would happen if we increase the number of steps by a factor of 2, say, effectively decreasing h by a factor of 1/2? How does that affect the error? It's not always clear how it's going to affect the error. There are general rules of thumb, you might say. Let me rerun the code with a value of h half as big, meaning I have to do twice as many steps, 900 steps instead of 450. So it makes a list twice as long. The value after time 45 minutes is 201.752. What's the error in this case? Again, phi of 45, 201.8, 201.8 minus 201.752, 0.048, about, here's a conceptual point, about half as big as that. That's important, what I just said there. I cut down the value of h by a factor of 1/2. I made it half as big from 0.1 to 0.05. And the error went down by about the same factor, from 0.096 to 0.048. Does that always happen? Well, not exactly, but in many examples, it happens approximately. If you decrease h by a factor of a half, the error will go down by about a factor of a half. If you decrease h by a factor of, say, 1/10, if you make it 1/10 as big by doing 10 times more steps as well, the error will go down by a factor of about 1/10 as well. Euler's method is something called the first order method. That's something you should know. Could come up on the final exam. And is related to the error-bound theorem. Let's look at the error-bound theorem now. So kind of a long theorem. Suppose f is continuous and satisfies the Lipschitz condition with constant L on a domain like this. What is this kind of domain? It's, think geometrically. Imagine a t-axis going this way and a y-axis going this way. T varies over some finite interval from a to b. Y possibly varies from -infinity to infinity. This would be what you call an infinite vertical strip. F is continuous on such a vertical strip and satisfies the Lipschitz condition in the variable y. It doesn't grow too fast in the variable y is effectively what that means we saw before. And that is important because we have seen examples, even simple examples, dy dt equals y squared, where your solutions have vertical asymptotes. And that should seem bad, at least for trying to apply Euler's method. If you got a vertical asymptote, how is Euler's method going to identify a vertical asymptote? It probably won't. And that a constant m exists such that the second derivative of your solution is always less than or equal to m in absolute value over the entire interval. You might wonder, excuse me, if we don't know the solution, how would we know this is true? And that's a good thing to wonder. I mean, we do examples where we can actually find the solution, but in many applications, you can't actually find the solution function, which is why you need something, a numerical method, like Euler's method or ultimately the Runge-Kutta method. So this is maybe a little bit of a mystery how you'd actually use this here. Where y of t denotes the unique solution of the IVP. Suppose these are your values of y, your approximations generated by Euler's method. Then this inequality is true. What's that? That's your absolute error, right? W of t or y of ti would be your exact value of your exact solution at the input ti. Wi is supposed to approximate that. That difference is the error, actual minus approximate. Take its absolute value. That's the absolute error. It's saying it's bounded by this crazy looking thing. H times m over 2L times, in parentheses here, e to the L times ti minus a minus 1. Ugh. M is a bound, upper bound for the absolute value of the second derivative of the solution. H is your step size. L is your Lipschitz constant. A is the initial value of t. Notice the A there. And ti is whatever value of t you happen to be thinking about to approximate the solution at. What's the proof of this? Should we study the proof? I think it is worth looking at, if for no other reason than to emphasize Taylor's theorem one more time in the course. Taylor's theorem. Taylor's theorem, I don't know if you really soak this in, but it's like in practically every section, at least when you're thinking about error terms, Taylor's theorem or some modified version of it is in there somewhere. There were modified versions when we were talking about Lagrange interpolation and that kind of thing. But it's applied everywhere in numerical analysis, including deriving the methods too. The second order Taylor method that we will review here in a few minutes uses it. There's also a fourth order Taylor method that we'll talk about that uses it as well. So I'm not going to completely understand everything in the proof, but let's try to get the basic idea. When I equals 0, the result is clearly true because, well, W of t0 equals W0 by definition of what W0 is. In Euler's method, W0 is defined to be alpha, the initial value of y. So that's 0, and this is something bigger than 0. Or 0 itself, actually, I guess. If ti equals a, you got e to the a minus a is e to the 0 is 1, 1 minus 1 is 0. You get 0 is less than or equal to 0 when I is 0. What about when I is bigger than 0? From equation 5.7, we have this is true. What's going on there? This is Taylor's theorem right here. Y of t is your, say, unknown solution function. We had an existence and uniqueness theorem that said such a function will exist and be unique under this kind of circumstance, like if there's a Lipschitz condition being satisfied. And we are assuming implicitly here that the second derivative of the solution exists, and in fact is bounded. So we are assuming it's second twice continuously, twice differentiable here. So you should be able to apply Euler's theorem or Taylor's theorem to y of t. This is effectively a Taylor expansion. It's not written in the usual way, right? Like in calculus, you write it most typically like this. You got some function f of x, not the same function as for the right-hand side of the differential equation, but I'm just talking about Taylor's theorem. In the abstract, you typically write it as, say, f of x0 plus f prime of x0 times x minus x0, plus if we're after just using the linear approximation, the error term is a second degree, f double prime at some unknown number c divided by 2 factorial times x minus x0 squared. That is effectively being used here, but with different notation. Instead of f of x, we have y of t. Y of t is like the f of x. Y of ti is like the f of x0. H, that's the same as this. That's the h. F of ti, y of ti, that's effectively like f prime of x0. Why? Because y of t is a solution of the differential equation. That thing right there, that's the same as y prime of ti. Because y of t solves the differential equation right there. That's where that assumption is being used. Plus h squared over 2, that's like, well, we got the y double prime of c, that's this. Dividing by 2 is the same as dividing by 2 factorial. H squared, that's this, that's the h squared. But here again, right there, that is where the assumption that y of t solves the differential equation is being used. And this is just the definition of Euler's method right there. And then they say, well, let's subtract these two equations. Why is that a good idea? Well, it's because we're after the difference y of ti minus wi. And on the right-hand sides of these equations, you've got that difference, y of ti and wi. So subtract these equations. Y of ti plus 1 minus wi plus 1, which is what this means, equals this minus this, right there, using new notation, plus this minus this. Both of those terms have a factor of h that can be factored out. Plus that thing gets just brought down here. And here's something fundamental for those who have not taken real analysis yet. The next step is using something called the triangle inequality. Those who've had real analysis know that they use the triangle inequality in that class practically every day. The triangle inequality most typically is written as the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. If a and b happen to be vectors and these absolute values are really lengths of those vectors, then you can actually draw a triangle, which is why it's called the triangle inequality, because you're saying the length of the longest side of the triangle is less than or equal to the sum of the lengths of the other two sides. The shortest distance between 2 points is along a straight line is effectively what that's saying. So it's actually a fairly clear fact if you draw a picture. For me, it's trickier than you might imagine, but it's true. And that's what's being used here. Take the absolute value of this. Yes, it will equal the absolute value of all of that, but because I have those sums there, I can break that into the sum of some absolute values as long as I put a less than or equal to. So the absolute value of this is less than or equal to the absolute value of that, plus the absolute value of this, plus the absolute value of that. The h is positive, so it can be factored out without an absolute value sign. H squared, of course, is positive as well. That can be factored out. 2 is positive. So you can write this. Now we use more assumptions. We know f satisfies the Lipschitz condition in the second variable y with constant L. So that means, I don't know if you remember the definition of a Lipschitz condition, that means this quantity is less than or equal to L for all possible values of wi, yi, and wi. You can bound this expression by h times L, which effectively is why you have that. Well, times yi minus wi, I forgot that part. And there you also have a yi minus wi, which is being multiplied by 1, which is why you get the extra 1 there. And we're assuming y double prime is bounded above by m in absolute value. The rest of the proof is getting from here to here, using seemingly some trickery. That trickery is in lemma 5.8, which is on the preceding page. It's kind of a weird lemma. It says if you got positive real numbers s and t and a sequence satisfying this condition, and suppose this is true, then this is true. But its proof, here we go. But its proof is understandable. You can work through this and understand it. Don't be too intimidated by this. What are they doing? They're just using the assumed inequality over and over again. AI plus 1 is less than or equal to that because I'm assuming that's true. Then AI is less than or equal to something similar, just change the subscript. That right there, I'm assuming that's true. Apply it, then simplify. Apply it again. AI minus 1 satisfies a similar inequality with changed subscripts. And you should check on your own that you will be able to simplify to this. And if you continue that pattern, you get this and this expression here, all calculus 2 beautiful memories. That's a geometric series, a finite geometric series whose sum is pretty easy to find. In calculus 2, we typically write the sum of a finite geometric series like this, just to remind you. A plus AR squared plus ... plus AR to the n minus 1 is the most typical last term written. Equals A times 1 minus R to the n over 1 minus R. You remember that from Calc 2? Maybe, maybe not. If your last term was A times R to the n, you would just make that exponent n plus 1 instead. It's the same idea. In this thing here, you could take the A to be 1 and the R to be 1 plus S. And actually, they don't actually use that formula until you get down here. And that simplifies. And then they use another lemma to say that this fact implies this fact. And that's where they get their final inequality. Now, I don't want to take the time to go through those details. You certainly could take the time to check all those details. And you could believe that they'll work. And they are all understandable. It's just a lot of details. What we want to do right now, though, is try to apply this theorem to our example at hand. So for our example at hand, f of ty is this function here. A is 0. We on Mathematica initially used h to be 0.1, then we also did 0.05. We did that 2 examples separately. What's L and what's M? Those are the only things we don't know yet. I think we should be able to figure out L by hand. I'm not so sure about M. There's my right-hand side function. What is L? L is a Lipschitz constant, which could be found by differentiating this with respect to y. Partial derivative of f with respect to y is going to be negative 4 over 10 plus 2t. We are considering this initial value problem over a specific finite interval of t values from 0 to 45. Because 45 minutes is when the tank fills up. T is going between 0 and 45. So what's the maximum value of the absolute value of this thing over that interval? It's a decreasing function of t here. So it's going to be maximized when t is 0. Maximized when t is 0, and its value when t is 0 is going to be 4/10. Max value when t is 0 is 4/10 or 2/5. 0.4. That can be used as the M. Oh, excuse me, not the M, the L, the Lipschitz constant. All right, you can look back in the definition of the Lipschitz constant, and also there's a theorem that says if you can bound the absolute value of the partial derivative of f with respect to y, then you can use that number as a Lipschitz constant. That's the L, 0.4. What's the M? Again, the M is an upper bound in the second derivative of your solution, which we do know in this case. It's the phi of t. We got to bound the absolute value of its second derivative. What's its second derivative? Probably kind of nasty. Yeah. Oh, no, okay, not as bad as I thought. And the absolute value of that equals itself. There's no negative sign there, and that's a 4th power, and t's positive anyway. And that is going to be maximized at t equals 0 as well. And have a value equal to what? 27,000 over 5 to the 4th is going to be its maximum value. That's going to be a decreasing function of t. 216 over 5, which is about 43.2. That can be used for M. You want to double check it, you could plot f double prime of t. It's maximized at t equals 0. And that maximum value is 43.2. So M can be taken to be 43.2, or if you don't like using a decimal, you could just go ahead and use 44. Could we get away with a smaller value of M? Probably. This error bound theorem, the bound here is going to be probably bigger than will be the actual absolute error. But if we're technically going to use the theorem, we need to use M equals 43.2 or bigger. So now using it, we can say the absolute value of y of ti minus wi, which if I use my phi notation is the same as the absolute value of phi of ti minus wi. It's less than or equal to h times m over 2l. And then it's times e, in parentheses, e to the l times ti minus a power minus 1. Plug in the numbers we found here. If h is 0.1, this is going to be equal to 0.1 times the L we found is, the M is 43.2. The L we found is 0.4. E to the 0.4 times TI. I'm going to leave TI as a TI. A is 0. (43.2) times 0.1 is 4.32. Divide by 0.8. We get 5.4 times e to the 0.4 TI minus 1. So, for example, what's the bound for the absolute error at y of t1? T1, by the way, is T0 plus H. That's 0 plus 0.1 is 0.1. A bound for the error at 0.1 will be 5.4 e to the 0.4 times 0.1 minus 1. Is this a small number or not? E to the 0.4 times 0.1 minus 1 times 5.4. This is about 0.22. Probably not as small as you'd like. But it is what it is. What about at T2? 0.2. You're going to get less than or equal to 5.4 times e to the 0.4 times 0.2 minus 1. E to the 0.08 minus 1 times 5.4. About twice as big. Ugh. Not so good. And yeah, you keep plugging in higher and higher values of TI, the error bound's not going to get any better. It's going to get worse and worse. But we know Euler's method did better than this, right? I mean, there was the fact that the true solution approaches a slanted asymptote in kind of a stable way, means that Euler's method in this case actually got better over time. But I think the error was smaller than this, perhaps significantly, even when t was small. Let's just double check and see if it was or not. So we were doing in the case where we were using h as 0.1. At 0.1, we get 193.2 for the estimate. The true value of phi at 0.1, 193.41. Sorry about this. Let's just do a few steps here. The error is 193.41 minus 193.2. We're actually not too far away from our error bound. Okay. 0.21's the error. Again, in this example, Euler's method is doing better over time because of the stability of the slanted solution. In general, Euler's method does worse over time the further out you go from the initial condition. How does it do at 0.2? The 0.2, 187.22. The error is then 187.22 minus 186.824. You see that up here? 0.396. So the error bound, even though it's kind of big, you might say, it's matching the fact that in reality, the error is kind of big. But if we went out all the way to 45, theta 45 minus W sub 450, the error bound theorem result would be humongous. You'd have to replace TI with 450. This would be a humongous number, but the actual error is pretty small. So the error bound theorem is just a guarantee. It doesn't mean you get a small number on the right side. But what if we didn't know the true solution? Is it possible to use this error bound theorem? Even if we don't know what y double prime is, because we don't know what y is? Yes, though I will tell you, if you do, typically the bound is even worse. How? It's related to the fact that we talked about last time, and the derivation we did last time for this Euler second order method. What was that derivation? That derivation was based on the differential equation, dy dt equals f of ty, and a solution satisfying that equation. The solution also satisfies a second order equation found by differentiating both sides of this with respect to t. And that's where the book writes f prime of ty on the right, but I think that's bad notation, so I'm writing this. Keeping in mind y is a function of t. Y is a function of t. And to do that derivative, you have to use the chain rule again, and it's the multivariable calculus chain rule. So you take the partial derivative of f with respect to t times the derivative of t with respect to t, which is just 1, so you don't have to write it, plus the partial of f with respect to y times dy dt. But dy dt is f of ty because y satisfies the differential equation. Everything here depends on both t and y. So I will more explicitly write that dependence in here now. So what this is really a second order differential equation that your solution has to satisfy. The solution of the first order equation also has to satisfy the second order equation. And this is y double prime of t, meaning if we can find a bound, an upper bound capital M for the absolute value of this, it'll also be an upper bound for the absolute value of that. And again, I don't know where the solution is. I don't know what the solution is, though I might have a guess approximately where it is based on a slope field. But if I truly have kind of no idea what the solution is, I might have to think about bounding this thing over an entire rectangle. In this case, the rectangle being t goes from 0 to 45 and y goes from 0 to 200. Can I find an upper bound for the absolute value of that thing over this box, this rectangle? Coming back to our example, let's have Mathematica do the calculations for us. Again, here is f of ty right there. What is this expression? Let's have Mathematica compute it. Find the derivative first of f of ty with respect to t. That's the way to do that. Plus the derivative of f of ty with respect to y times f of ty. And simplify. That function of two variables, we would then want to bound its absolute value over the rectangle. Let's just make a contour plot of it, of the absolute value of this. Copy and paste. Over the rectangle of interest, t goes from 0 to 45, y goes from 0 to 200. My guess is, without entering this yet, that the value of this multivariable calculus function over this rectangle is going to get pretty big. And so the m we would have to use based on this would be pretty big. Let's add lots of contours. Yeah, in fact, some weird stuff's going on there. I don't know exactly what's going on. It looks like the function gets bigger and bigger as y gets bigger, and is maybe growing so fast over here that the level curves are really close together. I'm imagining that this thing is maximized over this rectangle when t is 0 and y is 200. Oh, and how about that 43.2? Okay, that matched our 43.2 from before. So it's not giving us anything worse. I suppose you could say that's happening because our initial condition was y is 0 equals 200. If I was considering this over a bigger box, like y goes from 0 to 400 for some reason, if I decided to do that, then I'd plug a 400 in here and I'd get a bigger number. And the m would be 763.2. And that would be too big of a value of m to be useful, you might say. But I guess in this case, we are getting the exact same thing as before. And I guess that makes sense since our initial condition up in the upper left corner of the rectangle is also where this function is maximized. That's why we got the same answer. So that's the kind of, what I'm trying to hint at is this is the kind of thing you would have to think about if you didn't know what the solution function was, which is something that happens. Probably most important thing about this, though, is the fact that this upper bound is linear in h. So as h gets cut in half, the upper bound gets cut in half. As h gets multiplied by 1/10, the upper bound gets multiplied by 1/10. Big O of h, you might say, as h goes to 0. Euler's method is a first order method. The Taylor method of order 2 is a second order method. There's not a error bound theorem given in the book for the Taylor method. Oh, no, wait, excuse me, there was. Yeah, effectively it's this. We talked last time about the Taylor method of order 2, using to approximate the solution with step size h when your solution function is sufficiently continuously differentiable, meaning just nice enough. The local truncation error is big O of h to the n. So when n is 2, that's O of h squared. That would imply that if you cut your error in half, or your step size h in half, your error gets cut down by a factor of 4. H 1/2 squared is 1/4. If you cut it down by a factor of 10, multiply the step size by 1/10, the error should go down by a factor of 100. 1/10 squared is 1/100th. Let's try implementing that here and seeing that works. So this is going to be a quick review of the Taylor method. What do we want to do for the Taylor method again? It was more complicated. Though it does have a similar overall feel to Euler's method in the sense that you're doing this kind of iteration right here. But the function that h gets multiplied by is more complicated. Here's this expression when n is 2, which when n is 2 does simplify to that. There's your right-hand side function for the differential equation. H is the step size. What's f prime? F prime is the thing I just wrote down a few minutes ago. It really is that thing. How does that work out for our example? So again, here is f. Let's re-put this down here further. There's f. Didn't have to re-enter it, but we have the right-hand side for the second order differential equation. The first term was the derivative of f with respect to t. The second term was the derivative of f with respect to y times dy dt. We're talking about the multivariable calculus chain rule here. But dy dt is f of ty. Because y satisfies the differential equation. Simplify that. We already saw that expression just a few minutes ago. That was the thing that we made the contour plot of, the absolute value of that, and that was in the upper left corner was maximized. So what is this? This thing is the f prime in the Taylor method. So, you hanging with me here, okay? If we want to apply the Taylor method again for some value of h, like 0.1, we are going to be iterating a function. I called it last time tm2. T just keeps getting updated by adding h. W gets updated by taking the previous value and adding h times, in the book, the T2 expression, where that is that thing right there. So can you remember that? F plus h over 2 times f prime. F plus h over 2 times f prime. Use parentheses here. F of tw plus h over 2 times f prime is this thing, except change the y to a w. Right, this entire thing is the T2. It's f plus h over 2 times what the book calls f prime of tw. That T2 gets multiplied by h, and the result gets added to w. The old value of w plus the change. This thing's supposed to represent the change in w. All right, let's apply it now with nest list. We're iterating tm2, initial condition 0, 200. H is 0.1, so I'm going to do 450 steps. We get 201.8, pretty close, right? That was phi of 45. 201.8, exactly. So it looks like our error is 201.8 minus 201.801, negative 0.001, a smaller absolute error than Euler's method. And what's more, if I decrease h by a factor of 10, the error should go down by a factor of 100, or maybe I should just decrease it by a factor of 2 and make it go down by a factor of 4. Let's try that. 900 steps now. and to as many decimal places as it's showing the exact same result. Okay, maybe I should change my example. Let's let h increase. So here again was what we got when h was 0.1. We got an absolute error of 0.001. So if I doubled h, that's going to make the error worse, bigger. Make h 0.2 and do 225 steps. We should expect the error to be what in absolute value? If I'm doubling h, and this is an order 2 method, I should expect the error to go up by a factor of about 4. I should expect the final error to be in the ballpark of negative 0.004. Let's see if it is. Sorry, I'll for all the scrolling today. 201.8 minus 201.806. Okay, negative 0.006. I mean, it's not, these are just rules of thumb. It's not exactly this, what you would expect. But as h gets smaller, it does tend to follow the rule of thumb better. If you decrease h by a factor of 1/10, say, you would expect the error to go down by about a factor of 1/100th.